Okay. So we had discussed briefly about what are the typical governing equations that we are going to encounter during our course. Means what are the basic governing equations which basically model the fluid flow and heat transfer and other type of species conservation, other type of conservations. So these equations are the equations that we need to solve to obtain the variation in temperature, velocity with space and time. So that is the aim of this of any CFD algorithm, to find different ways of solving these governing equations to get the solution for temperature, velocity, and any other property that is required. And we saw that all these equations are of similar form. They are second order partial differential equations. Okay. So now what we are going to do is we are going to go into a brief detail of second order partial differential equation, because the nature of the PD, partial differential equation, the nature of the PD is going to dictate what type of solution algorithm is best suited for that equation. Okay. So depending on the nature, we will see that there are three types of PDs for our case. Okay. So there can be many types of classification. So we will classify in a way where we will have three types of PDs: elliptical PDs, then parabolic PDs, and hyperbolic PDs. And for each of them, the nature or the behavior is different. As a result, if we develop algorithms which suit this behavior, it is much more beneficial. It is easier to solve the problem. Okay. So that is why we want to study a little bit about second order partial differential equations and their classification. So in case you have forgotten about what are PDs, you must have studied before in the beginning of your engineering, or say in the beginning of BSc, basically in the beginning of your bachelor's. But in case you have forgotten, let us just revise once about PDs. So PDs are equations with a variable which is a function of more than one independent variable. Okay. So at least two, which is a function of at least two independent variables. So for example, I have a variable phi. If it is only a function of x, so if phi is equal to phi x, then if there is a differential equation based on that, I cannot call it a PD. Okay. It will be ordinary differential equation. So if the phi is a function of say x and y, and then there is a differential equation based on that phi, then it becomes a PD. So equation with a variable which is a function of more than one independent variable and with at least one partial derivative of that function. So at least one partial derivative of that function needs to be there in the equation. Obviously, otherwise it's not a partial differential equation without any derivatives, right? It will become an algebraic equation. So for it to be a differential equation, that to a partial differential equation, you need at least one partial derivative of that function. So let us take a look at some of the most common examples. We already know these examples. So first is very famous example, this one. Del square u del x square plus del square u del y square equal to 0. This is known as, what is this equation called? Very, very common equation in Laplace equation, right? So Laplace equation is a second order PD. We will come to what is order of PD, but it's a PD because u is a function of x and y, and there is at least one partial derivative of u. Here there are two partial derivatives of u, but at least one is there. So this is a PD. Del t equal to alpha del square t del x square. 1D transient heat conduction equation. Okay. So transient because there is variation with time, and conduction term is also there. So it's 1D transient heat conduction equation. So there also temperature is a function of two independent variables, time t and space x. So because it's a function of two independent variables and at least one partial derivative is present, so it's again a PD. Here again there are two partial derivatives that are present. But even if it was del t equal to say constant, but t is a function of time and space, then also it would have been a PD. Another example, del phi del x equal to 0, where phi is a function of x and y, okay, where x and y are independent variables. So if phi is a function of x and y and del phi del x equal to 0, this at least one partial derivative of phi is there, and it's a function of more than one independent variable, so it's a PD. Okay, so when we integrate this PD, we will get a solution of this form. Why I am showing this? Because I want to show a distinction between another equation which is not a PD, okay, ordinary differential equation, but looks of similar form. Okay. So in this case, if we integrate phi for phi will become equal to function of some function of phi plus C1, where C1 is a constant. This has to be obtained by using boundary conditions, additional conditions. So basically, this tells that there is no variation with x, but there can be variation with y. Okay. On the other hand, if I have an equation like this, d phi dx equal to 0, okay, where phi is only a function of x, in that case, it's a ordinary differential equation. It's not a PD. Okay, and the solution will be different. If you integrate this, you will just get phi equal to some constant. Okay, because it's not a function of y. So that's why these two equations are very different. One is a PD, one is not a PD. So we will know when it is a PD because if we know whether phi is a function of more than one variable or not. So there are some important terms here. Again, these things should have been taught to you long back, but let us just revisit them once to refresh our memory. So order of PD. So what is the order of PD? The order of the, use this, it's too large. What is the order of PD? Order of PD is the order of the highest derivative term in the equation. Okay. So here the highest derivative term is this second order term and this second order term. So this is a second order PD. Here the highest derivative term is this second order term. So this is also second order PD. This is a first order PD because the highest derivative is of first order. Okay. So the order of the highest derivative term in the equation. So based on that, we define what is the order of a PD. Okay. Let us again look at a few examples. I'm just going through multiple examples just to refresh our memory. So del u del x plus del u del y equal to 0, where u is a function of x and y. It's a first order PD because the highest order term is first order. So these are also denoted derivatives. Partial derivatives are also denoted in this way. So del u del x can be written as ux and del u del y can be written as uy. If there was a double derivative, del square u del x square, you would have written as uxx. If there was a double derivative, del square u del y square, we would have written as uyy. If there was a double mixed derivative, del square u del x del y, we would have written as uxy. Okay. This is a form of notation which simplifies the writing, means which takes less time to write, so but has the same meaning. Okay. So we can also write this PD as ux plus uy equal to 0. Similarly, let us take a look at another example, del square u del x square plus del u del x plus del u del y plus c equal to 0. Here the highest order term is this term, which is second order. So this is a second order PD. Again, as I was explaining, this can be denoted as, so this term is uxx plus ux plus uy plus u equal to 0. Okay. So this is the order of the PD. Order of the PD is very important because the solution will depend on the order of the solution, and the solution method will depend on the order of the PD. And for most of our heat transfer and fluid flow problem, we encounter second order PDs, as we have seen in the previous class. So the highest derivative is second order derivative. Okay. Now, let us define another term, principal part of a PD. Okay. All the terms that contain derivatives of order equal to the order of the PD constitute the principal part of the PD. Okay. Again, let us try to understand. So there is a PD where there are some second order terms, some first order terms, some zero order terms, means zero order derivatives. So all the terms which are second order will together constitute the principal part. If it's a first order PD, then all the first order derivative terms will constitute the principal part of the PD. If it is a third order PD, then all the terms which are third derivative terms will constitute the principal parts of the PD. Why we are isolating this principal part? We will see later that the principal part of the PD plays a major role in determining the, or in classifying the PD, or in determining the solution algorithm, or the nature of the PD. How the variable, say in this case the variable is u, how this variable u behaves with the independent variables x, y, or t. This depends strongly on the principal part of the PD. So as a result, we want to isolate and study this principal part of the PD because it is of such a high importance. Okay. So we can write a general second order PD in this form, where all the terms, if all the terms are present, all the possible terms are of this form: a del square u del x square plus b del square u del x del y plus c del square u del y square. Okay, these are all the second order terms possible. Then all the first order terms, d del u del x plus e del u del y. Then f u, okay, equal to g. So these are all the terms possible where a, b, c, d, e, f, and g are constants. So here the principal part of the PD is all the second order terms. So a del square u del x square plus b del square u del x del y plus c del square u del y square. Okay. So these are the, this part constitutes the principal part of the PD. Coefficients of principal part can be used to classify the PD. Okay. So based on these coefficients a, b, and c, we can classify the nature of the PD based on the, so we can understand what is the nature of the PD. It will depend on the coefficients a, b, and c. So so just to reiterate, you don't have to take down notes because all this I am sharing in the Teams portal already. It is shared, so you can just download from there and study. So just you can focus on the lecture and try to understand and ask questions. So the screen is still visible to you, right? And I'm still audible.
Yes, sir.
Okay.
Sir.
So now let us take a look at another definition or another classification: linear PD and non-linear PD. Okay. So if all the coefficients of the dependent variable, here what is a dependent variable? So this is the general PD, second order PD. Dependent variable is u. U is a function of x and y, which are independent variables. So x and y are the independent variables. And we are writing the derivatives of the dependent variable u in terms of the independent variables x and y. Okay. So if the coefficients of the dependent variable, say this dependent variable is u or phi or t, whatever, if the coefficients are all independent of this variable itself, then it is a linear PD. Okay, so in this case, if a, b, c, d, e, f, g, they are not g. Okay, so a, b, c, d, e, f. So if they are not function of u, then it is a linear second order PD. Okay, if any one of them is a function of u, if a or b or c, say this term is u del square u del x del y, then it becomes a non-linear PD. Or this term becomes u into u, say u square, then it becomes a non-linear PD. Okay. So if the coefficients are of the dependent variable at all independent of the same variable, then it is a linear PD, otherwise it's a non-linear PD. Why we are classifying this? Because solving a linear PD is much more simpler as compared to solving a non-linear PD. For non-linear PD, because the coefficients itself are function of the unknown variable, we have to resort to iterative methods. Means we have to iterate again and again to get to the correct solution. Unlike the case of linear PD in CFD algorithms. Okay. There may be ways to directly solve them analytically, but we are not focused on them. Our course is on numerical solution. Please hold for a second. All right. So let us take a look at some examples again to reinforce this concept. So uxx plus 2uxy plus uyy. So because they are double derivatives, this is a second order PD plus ux plus uy plus u plus xy. Okay, this is a linear PD. None of the coefficients are functions of u. Okay, although there is a like xy term, but it does not matter. It's not a function of. It's not nonlinear in u. Okay. Similarly, this 1D heat conduction, transient heat conduction problem. Okay, 1D transient heat conduction problem. Del T equal to alpha del square T del x square. It will become linear if alpha is independent of T. Okay, if alpha is constant, alpha is the diffusivity, right? For the math students, I'm saying. Obviously, other students know. So, if the diffusivity is independent of temperature, like it's a constant material property, then this is a linear second order PD. If the diffusivity alpha is a function of temperature, which happens for most materials, then it becomes a non-linear PD. Okay, it will depend on the coefficient alpha. Similarly, ux del square u del x square plus del square u del x del y equal to 0. This term is non-linear because the coefficient has u in it. Okay. Del square u del x square plus del u del x whole square. Okay. The coefficient of del u del x itself is del u del x. So it is non-linear. Similarly, del u del t plus u square equal to 0. Coefficient of u is u. So it is non-linear. Okay. Del square u del x square plus a sin u. Okay. This is non-linear. This may not become clear to you directly because sine function is non-linear. This becomes non-linear. Okay. So if you write the sine function in terms of series, it will become a non-linear term. Like there will be non-linear terms. So sine is non-linear function. So this is also a non-linear PD because of the sine function. So generally we classify a PD. Means not this. Generally we say describe a PD or call a PD based on whether it is linear or non-linear, whether what is its order. Okay, and based on that. So for example, this PD del u del t plus t del u del x. So I'm just showing through some more examples to clear the concept. So this is linear if we assume that t is not a function of u. This is linear first order PD. Okay, like this we will call our PDs. So this is a linear second order PD, del square u del x square plus del square u del y square. So Laplace equation is a linear second order PD. Del u del t plus u del u del x equal to mu del square u del x square plus s. This is a non-linear because of this term, non-linear second order because of this term, non-linear second order PD. Okay. So I hope these things are clear now. We have seen what is a PD, what is the order of PD, what is the principal part of PD, what is linear and non-linear PD. Okay. So linear problems are easier to solve, as I have already mentioned. Non-linear problems need iterative solution for numerically solving them. Okay. So we are bothered with numerical solutions. So for numerical solution, we need iterative schemes. Any questions? Okay, let us move forward. Significance of second order PD. So why we are bothered with second order PD? Because most of the fluid flow and thermal problems are governed by second order PD. Okay. So it is not that, see, the thing is that the physical phenomena is independent of whatever is the equation or not. Physical phenomena is a physical phenomena. It does not bother with what equation is needed for that. So it is already existing in nature. So all the equations that we use to describe a physical phenomena are actually some sort of models to capture the physical phenomena in the best way. For example, when we say the 1D transient heat conduction equation, we have found that that is the best way to describe or capture the transient heat conduction equation. So when we say that Navier-Stokes equation or fluid flow equations for flow, what we mean is that this is the equation that we found to be best suited for describing the flow phenomena. It is not that flow needs to be governed by this. Flow was occurring anyway in nature before, like without or with the knowledge of equations. So it is not bothered with equations. But these equations are the best suited models for any physical phenomena. Similarly, if we go beyond heat transfer and fluid flow, say the extension of a spring due to a force, F is equal to Kx, where F is the force and X is the say elongation, deformation of the spring, and K is the spring constant. So this is just a model. We have found that this model suits the elongation of the spring perfectly. So whether there was a model or not, that does not matter to the spring. Whether so because it will elongate in the way that nature dictates, that the physics of this universe is works. So these equations are only like the most appropriate models that we are fitting to some natural phenomena. Okay. So what we have seen is that many of the natural phenomena related to heat transfer and fluid mechanics can be modeled using second order PDEs. Okay. So we saw that in nature fluid flow is occurring. We found what is the best way to describe the phenomena, what captures more accurately this phenomena, all the variations. We found that it is a second order PD, which we are calling as Navier-Stokes equation. Similarly, heat conduction equation. Okay. So classification of second order PD becomes very important because we want to understand this physical behavior, and we know that the physical behavior depends on the nature of the PD. Okay. So for all these different types of fluid flow and heat transfer problems, we want to understand the physical behavior, and based on our understanding of the physical behavior, we want to develop our numerical algorithms. We don't want to arbitrarily develop a numerical algorithm. We want to tune our numerical algorithm so that it is best suited for a certain type of the physical behavior or certain type of physical phenomena. That's why we want to classify our second order PDs in such a way so that it gives us some information regarding the nature of the physics, like the behavior that is happening. So there can be hundreds of different types of classification. For example, PD we have already classified as linear and non-linear. Okay, that also there was some purpose. The purpose was to find out whether it is easier to solve or difficult to solve, or whether the solution technique will be different. Similarly, we want to do another classification which will tell us something about the nature of the solution or nature of the behavior of the dependent variable. Okay. And this we will just apply for only second order PDs. Okay, only second order PDs. For first order and third order PDs, this discussion is not valid. There can be similar classifications, but that is beyond the scope of this course. So let us consider again the general equation. General second order PD: A del square U del x square plus B del square U del x del y plus C del square U del y square plus D del U del x plus E del U del y plus FU plus G equal to 0. All the terms are present: second order terms, first order terms, zero order terms, constant. Okay. So now the classification can be made for this PD based on the coefficients of its principal part. Principal part we know is the highest order terms, constitutes the highest order terms. So in this case, principal part is A del square U del x square plus B del square U del x del y plus C del square U del y square. So the coefficients are A, B, C. So for these coefficients, if B square minus 4AC is less than 0, okay, we will see why is this classification like this. But at this moment, just go with me. So if B square minus 4AC is less than 0, we call the PD as elliptic PD. Okay, and it means that there are no real characteristic lines. At this point, you do not know what is a characteristic line. If you may know, but based on this course, you do not know what is a characteristic line. We will study subsequently. But let us note at this point that for elliptic PDs, there are no real characteristic lines because B square minus 4AC is less than 0. If B square minus 4AC is equal to 0, we call the PD as parabolic PD, and it has only one real characteristic line. If b square minus 4ac is greater than 0, we call the PD as hyperbolic PD, and it has two real and distinct characteristic line. Okay, two real and distinct characteristic line. So this is valid only for second order PDs like this. Okay, this discussion. Do not try to apply this to other types of PD. So, for example, first order, we'll see an example later, maybe in the next class or next to next class. That first order PD can also, like, it can be a hyperbolically, but you cannot use this format b square minus 4ac to find that. So what is a characteristic? I'm saying that there are no characteristic or one characteristic or two characteristics. So what is a characteristic of a second order PD? So again, if we have a general PDA like this, the partial derivatives of the highest order are this uxx, uxy, and uyy. Okay, these are the highest order partial derivatives, second order partial derivatives. So in the domain of solution, so if we may have a certain domain of solution. You are solving a heat conduction problem. The domain may be in the x direction, it may be from 0 to 1 meter. In the y direction, it may be from 0 to 2 meter, whatever. So the domain is from some, so it is some distance along x and some distance along y, or some distance along time t. Okay, distance means here a temporal distance. So within this domain, the second order derivatives may or may not be continuous. Okay, so please note that these are second order derivatives. I am not talking about the variable u. Variable u is continuous, but the second order derivatives may or may not be continuous. See, if there are lines across the domain where the second order derivatives or the highest order partial derivatives, here the highest order of second order. So there are maybe lines across which the highest order partial derivatives are not continuous. These lines are known as characteristics of the second order PD. Okay, let me reiterate this point because students get confused here. So there is a domain where you have a variable u, which is a function of xy. In this case, it is a function of xy. Okay, so this u may be continuous, but its second order derivatives of u, so which are uxx, uxy, uyy, this type of derivatives, they may not be continuous across the entire domain. There may be line across the domain, may or may not be. There may be line or may not be any line across which these derivatives have a sudden jump. They are not continuous. Okay, or on that line there is no solution for the second order derivative. Okay, so these lines are known as characteristic lines, and they actually govern the physical behavior, as we will see later today. They govern the physical behavior of the physical phenomena. Okay, for in this case, how u varies or how u is influenced by some changes, that is governed by these characteristic lines. Okay, so the important thing to note here or point here is that don't get confused that u is discontinuous. U is continuous. The second order terms are discontinuous. Okay, across these characteristic lines. These are important for developing proper numerical solution technique. Let us try to see why this minus 4 is less than 0. Why we have classified like this, elliptic, parabolic, hyperbolic, and why we are saying that there is no real characteristic if b square minus 4ac is less than 0. Okay, let us try to understand this. So what we will do is, because our interest lies in the principal part, we will put all the other terms. Okay, we will bundle all the other terms together in a single term. Let us call this as h. Okay, all the other terms, this dux, uy, fu plus g, all this let us put together in h. So our equation can be written as auxx plus buxy plus uyy plus h equal to 0, where h contains all the other terms which are not second order terms, which are not the principal part. So let us call this equation as equation 2. This equation is equation 1 for reference. Okay. What I'm going to do is I'm going to keep this open. Because I want to refer back to the previous equations. We will keep this open here on the right hand side and discuss on the today notes on the left hand side. So this is equation 2, okay, which is same as equation 1. We are just writing in a different way. Now, as we know that u is a function of x and y, okay, the dependent variable u is a function of x and y. Let's go like this. We can write u is equal to uxy. It's just a way of denoting that it's a function of xy. So the first derivative, partial derivative of u, we can write as ux is equal to uxxy, or dux we can write as del u x del x dx plus del u x del y dy. Okay, any variable. So it's a phi, which is a function of xy. We can write d phi as del phi del x dx plus del phi del y dy. Okay, that is basic maths. So because ux is a function of xy, we can write dux to be del ux del x dx plus del ux del y dy. Okay, or dux is equal to uxx dx plus uxy dy. Let us call this as equation 3. Similarly, u is a function of uxy, means it's a function of xy. So uy is equal to uy xy, means uy is a function of xy. So duy can be written as del uy del x dx plus del uy del y dy. Again, remember that if phi is a function of xy, we can write d phi as d phi is equal to del phi del x dx plus del phi del y dy. Okay. So same here, duy is equal to duy dx del uy del x dx plus del uy del y dy. Okay. Or duy is equal to uyx dx, okay, this derivative, plus uyy dy. Because uyx and uxy will be similar, okay, same basically. So duy can also be written as uxy dx plus uyy dy. Since order of the derivative does not matter, dy is equal to uxy dx plus uyy dy. Let us call this as equation 4. Okay. So now we can put these three equations together, 2, 3, and 4, in matrix form. Okay, we can organize this equation in matrix form. What is our aim? We are trying to find out the characteristic of the second order PD. Okay, it will be clear in a moment. So in matrix form, this looks like this. So I will keep all the three equations. Okay, here for reference. First equation is this one, right? So AUXX plus BUXY plus CUIY is equal to minus H. This is the first equation. Second equation is dx into uxx, okay, dx into uxx plus dy into uxy, okay, plus 0 into uyy, because there is no uyy term, is equal to dux, which is on the other side. Okay. Similarly, the third equation, this equation, there is no uxx term, so 0 into uxx plus dx into uxy, this term, dx into uxy, plus dy into uyy, this term, dy into uyy, is equal to duy, this term. Okay. So obviously, you know matrix multiplication, this into this plus this means it goes like this. So this into this is equal to this. Second row into this column is equal to second term. Third row into this column equal to third term. Okay. So this is in the matrix form, all the three equations. This is of the form ax equal to b equal to 0. Sorry, ax equal to b, where a is this coefficient matrix a, b, c, dx, dy 0, 0, dx, dy. X constitutes the three second order partial derivatives uxx, uxy, and uyy. Okay, so you can see that these three partial derivatives are there in x. Okay, and b is the this term minus h dux and duy. Okay, so we want to know when the solution of this equation ax equal to b does not exist. Okay, let me open the matrix form now. We want to know when the solution of this does not exist. Why? Because solution does not exist means uxx, uxy, and uyy, we cannot find the values. So there may be some location where we cannot find the values of uxx, uxy, and uyy. It means that they are discontinuous at that point. That means that those points constitute our characteristic line. If we can find some point where the solution of uxx, uxy, and uyy are not does not exist, then we can call that as the characteristic line. Again, I will reiterate that this is the discontinuity in the second order term, not in the variable u itself. Okay, a lot of students every time they get confused that u itself is jumping. It's not that. So if it is a temperature, there is no jump in the temperature value at the characteristic. There is a jump in the second order derivative of temperature. Okay, if the temperature is the dependent variable. So anyway, we want to know when the solution of the equation Ax equal to b does not exist. So when does it does not exist? When does the solution not exist of this form? Can anyone tell? When does the solution not exist?
Sir, when the matrix is singular or the determinant is zero.
Correct, correct, good. So if the determinant of A is 0, the solution will not exist, because we can write the solution as x is equal to so inverse of A into B. Okay. So if the determinant of A is 0, we cannot find the solution. So the solution does not exist. So now our problem has become like our problem has been reduced to a problem where we want to find the case where the determinant is 0. Okay. So just again, just summarizing what we have discussed. For our case, we want to know when the solution of uxx, uxy, and uyy does not exist. We have already discussed this. This is just when you are reading the notes, you will have some more information. So when there is a discontinuity in the value of uxx, uxy, and uyy, the solution does not exist in physical terms. So we want to find out when this happens, because that will give us the characteristic lines. Okay. Let us try to understand. Already you have said correctly, but let us try to understand with a simple example, so that others who are not very clear, they also understand why the solution does not exist in that case when this determinant is 0. So let us consider a couple of equations. Okay, not PDEs, normal equations, algebraic equation. X plus y equal to 1 and 2x plus 2y equal to 3. So you can, by looking at the equation, you can tell that there is no solution. Okay, because x plus, based on the first equation, x plus y should be equal, 2x plus 2y should be equal to 2. But the second equation tells that 2x plus 2y is equal to 3. It means that there is no solution for these two equations. Okay. So in this case, it is obvious that solution does not exist. So we can write this in matrix form. My throat is hurting me today. Just a second. I have a little bit of throat infection, so it's causing me problem. Anyway, let us continue. So if we write this in matrix form, we can write this as 1 into x plus 1 into y is equal to 1, and 2 into x plus 2 into y is equal to 3. Okay. So this is of the form, same form what we have just studied, ax equal to b, or x is equal to a inverse b. But a is given as 1, 1, 2, 2. Okay. So determinant of a is 0. So 2 minus 2 is 0. So that's why we find that solution does not exist. So we can mathematically also prove that the solution does not exist because the determinant is 0. So you can see from the simple example that if the determinant is 0, the solution will not exist. Okay. So for our case also similarly, what was our equation? This is our equation. Okay. So the determinant, if we find the determinant of this, and if this is 0, then the solution of uxx, uy, and uxy will not exist. Not the solution of u. Again, I am reminding already 3-4 times because every time students get confused. So the solution of uxx, uxy, and uyy will not exist, but obviously solution of u will be there. It is the solution of the second order terms that will not exist at those points. Okay, not the actual solution of say u or any other variable. So if the determinant, so determinant is determinant of abc dx dy 0, 0 dx dy of this. If it is equal to 0, then uxx, uxy, and uyy are continuous when this condition is satisfied. So this condition will be satisfied only at certain points, may or may not be satisfied, and we will, if we find the location of those points, we know that at those points the determinant is 0 and the uxx, uxy, and uyy do not exist or are discontinuous. Okay, so those points will constitute lines which we will call as characteristic lines. One interesting thing or important thing to note here is that only coefficients ABC are important and part of this. You can see only the coefficients ABC. There are a lot of other coefficients, right? D, E, F, G. All these have not come into the equation. Okay. All the other coefficients are absent. They do not play any role in determining the nature of the second order terms of the nature of the PD. Okay. Second order PD. So let us equate this to 0. So A into dy square minus 0, okay, plus b into 0 minus dx dy, this term, plus c into dx square minus 0 into dy. So c into dx square equal to 0. Okay. So this is when the determinant is 0. Again, just only coefficients of highest order derivatives matter for the characteristic of PD. So we can rewrite this as a del dy dx whole square. If we divide all the terms by dx square, a dy dx whole square minus b dy dx plus c equal to 0. Okay, by dividing all the terms by dx square. It's wrongly written here. Anyway, the solution of this quadratic equation is what? The solution of this for this dy dx. Okay, it's a quadratic equation for dy dx, right? So it is like ax square plus bx plus c equal to 0. So solution is dy dx is equal to minus of minus b. So this will be plus. I have written here plus b. Please note that this will be plus. Okay. Minus of minus b plus minus b square minus 4ac by 2a. Okay. So if dy dx is equal to plus b, so this will be plus b. If dy dx is equal to plus b, plus minus b square minus 4ac by 2a, then the determinant is 0. And for those points, we will have discontinuity in the second order terms, and those points will constitute the characteristic line. Okay. So what points? So points where dy dx, where x and y are space coordinates or independent variables. So where x and y satisfy this condition, dy dx is equal to b plus minus b square minus 4ac by 2a. Okay. So let us now take a look at a few cases. Say b square minus 4ac is less than 0. Okay. Then the square root of this is a negative term inside the square root. So there is no real solution for dy dx for this case. It will lead to a complex number. So there the dy dx do not have any real solution if b square minus 4ac is 0. So because dy dx does not have any real solution, so they are in the domain, there are no points where this condition is satisfied, that dy dx is equal to this. Okay. So no real solution exists. So there are no characteristic lines in the domain. Okay. If b square minus 4ac is less than 0. So this type of equation we call as elliptic equation. We have already seen this form, b square minus 4ac is less than 0. Now we are finding why for this case there are no characteristic. Okay. Because we are finding that dy dx does not have any real solution. If b square minus 4ac is 0, this term is 0, then you have only one solution. Okay, only one real solution, only one distinct real solution. So it means that there is only one real characteristic. Okay, So there is only one dy dx is equal to, like, only one equation of this form, dy dx is equal to some value. And this type of equation we will call as parabolic PD. Okay, we'll see what is the nature of this later on, elliptic and parabolic, how the nature varies. But this type of equation is parabolic PD. Now we understand why there is only one characteristic. If b square minus 4ac is greater than 0, then you will have two equations. Dy dx is equal to b plus b square root over b square minus 4ac by 2a, and dy dx is equal to b minus root over b square minus 4ac by 2a. So there are two real solutions possible. So it means that there are two real and distinct characteristics. Okay. So anyway, you will see that this is actually equation of line. Dy dx is equal to something. This gives the slope of a line. Okay. So this means that there are two characteristic lines for hyperbolic. For this case, where b square minus 4ac is greater than 0, we will call this as hyperbolic PDs. Okay. So the important point to note here is that it is only valid, this classification is only for second order PD. Okay, we have done this discussion only for second order PD because this is relevant for us. Second order PDs are relevant for us for our fluid flow and thermal problems, and our course is on computational methods for thermal and fluid flow problems. That's why we are bothered with this. Questions? I will ask questions if you are not asking. So if the, say there is a characteristic line, okay. Okay, I will ask later, not now. I want to discuss something so that you have a better understanding. So we will take a look at a few examples, okay, today and in the next class, 4 or 5 examples to reinforce this idea about these characteristic lines and nature. Okay. So let us take a 5 minutes break at this point, and then we will continue our discussion after that. Okay, can you hear me?
Yes, sir.
You can see the screen also, right?
Yes, sir. Yes.
Okay, let us then continue. Okay, so we have seen a classification of PD. Please note that this is plus sign. In the file that I have uploaded, I think I've wrongly uploaded the previous version. No, I have not yet uploaded. Okay, it's good. So let us continue. So we have seen a classification, a type of classification which we are assuming will be helpful for our to give us an understanding of the physical behavior of a say PD, or a physical behavior of a problem which is governed by a PD, like the heat transfer problem or a fluid flow problem. Okay, so we will see a few examples to find out actually how this classification helps us, or how this classification is related to the actual physical phenomena that is occurring. So the question is, what is the physical significance of this classification for our fluid and thermal problem? It is fine that we have developed some classification. How do I hide this? It is fine that we have developed some classification, but what is the use for us? Okay, why have we developed this classification? Let us take a look at a few cases. We'll start with the simplest case, which is encountered very frequently in engineering applications. Okay, in lot of physical phenomena, which is the Laplace equation. Del square phi equal to 0. In general, Laplace equation, which is del square phi del x square plus del square phi del y square in 2D, that is equal to 0. If it is a 1D equation, it will be del square phi del x square equal to 0. 3D, it will be del square phi del x square plus del square phi del y square plus del square phi del z square equal to 0. So we are bothered with 2D equations here. So for us, Laplace equation is uxx plus uyy equal to 0. Okay, for 2D. And this is one example of this is the steady state 2D heat conduction equation. Okay. So del square t del x square plus del square t del y square equal to 0. This is a steady state heat conduction equation. Means this governs the conduction when there is no variation with time. Okay, we can find the temperature profile in a domain along x and y based on this equation, and boundary conditions based on boundary conditions. So this is a PD, second order PD, right? Second order terms are there, and t is a function of x and y. So more than one independent variable. So what is the nature of this? So the coefficients are 1 into txx plus 0 into txy. There is no txy term, plus 1 into tyy equal to 0. Okay, let us open the classifications on this side. Okay. So if we write in this form, we keep this open. So for this form, a is equal to 1, b equal to 0, and c is equal to 1, or b square minus 4ac is minus 4. Okay. So because it is less than 0, this is an elliptic equation. Now the question you should ask is, it is all fine that we have found that it is an elliptic equation based on our calculation. But so what? What is the meaning of whether it's an elliptic equation or not? How does it matter to us? We have found that okay, you have shown some classification, and based on some calculation, we have found that B square minus 4ac is less than 0. So we are calling it elliptic equation. But so what? Okay, what is the physical significance of this? So that is an important question. Okay. So let us consider a physical problem, okay, to try to understand the significance. Remember that for elliptic equation, we have discussed that there are no characteristic lines. Okay. So let us come back to this. So there is a domain. Say it is we are considering a heat conduction problem, and a domain given like this. Okay. So where the temperature can vary from say x equal to 0 to some x value, and from y equal to 0 to some y value. So this is our domain of solution. It can be like a plate. You can consider it like a metallic plate or something like that. Okay. So now say the domain is at same temperature everywhere at the beginning of the solution. Now if I put a perturbation or a source term or a disturbance somewhere around in the domain, okay, say at point P I am putting a new value of temperature or some heat source, some disturbance, some fluctuation I am putting, okay, some heat source or some new value of temperature. Say everywhere temperature is 300. Suddenly I am saying that at this point temperature has to be 400. Okay, so some disturbance or some change I have put. So what this equation means that for 2D steady state heat conduction, for this equation, this change will be felt in the entire domain immediately. So the information that some perturbation has occurred here, some disturbance has occurred here, will travel to all parts of the domain at infinite speed. Okay. So the source term causes a disturbance at point P, which travels in all directions. It will travel in all directions. This is important, all directions, because we will see that in some cases it may not travel in all directions. It may travel in only one direction. But in this case, the information will travel in all directions from P at infinite speed. Now you can say that, sir, I have, if we put a source term, heat source or something, will it not take some time to for the temperature to change at the other points? If I put a heat source here, and if it is a physical problem, metal sheet is there, it will take some time for the temperature at other points to change, right? That is true for a transient problem, but we are assuming, we are trying to find out the steady state solution. Okay, steady state, what will be the solution? So without this disturbance, the steady state solution was 300 Kelvin everywhere. Now with this disturbance, the steady state solution has to change everywhere immediately, right? Steady state solution is a single, like it's not changing with time. It's a final solution. So immediately all the other values should change in the like, if this is 400 and the boundary is still at 300, maybe this point will become 380, this will 360, 340. So the solution will immediately change because of this disturbance. Okay, it means that that information has passed at infinite speed to all the points in the domain. Okay. In another way, we can tell this: all the points in the domain will feel the effect of disturbance or change instantaneously. And the second thing is that if there is any change in anywhere in the domain, any change, any other change, this point P will immediately feel that change. Okay. If there is any change anywhere in the domain, this point P will also immediately feel that change. Okay. So let us just go to summarize this. All points in the domain will feel the effect of disturbance change instantaneously. Any change at P point influences the value of all other points of the domain instantly. Okay. All the other values will change. Any changes at any location in the domain will affect the temperature at P instantly. Both way it is, like both way information is traveling. P will also influence all the other points, and all the other points will also influence P if there is any change. Okay, so information can travel freely across the domain. There is no restriction. Okay, so this means that there is no discontinuity or like no restriction for the information to pass from one side to the other. Again, discontinuity does not mean discontinuity in temperature. Even if there is restriction, we will see later, temperature may remain constant. It is only discontinuity in the second order derivative, and here there is no discontinuity in the second order derivative. As a result, this information can pass everywhere instantly. Both ways, means from the point P to all other points and from all other points to P. Okay. In mathematical term or in our, please switch off your mic. So in mathematical term, it means that variation of T or solution of T is smooth. Okay. So this is somewhat confusing. Actually, there won't be any jump in T in the domain. It's that there is no discontinuity in the second order terms. Okay. So for the solution algorithm for solving an elliptic problem should ensure that for any point P, so this is important, what I've written in red here. For any point P, the calculation of T should include the information from all the neighboring points, from all the direction. Why? Because the disturbance signals or disturbing signal propagates in all directions. So if I am developing a solution algorithm, if I cannot minimize this. If I'm developing a solution algorithm, okay, you will see later that, or I have discussed in the introduction classes, that we divide the domain into number of subdomains, control volumes or grid points. So for this, each point, so for say one control volume or one grid point is P. Okay. So when we try to calculate the temperature for P, our solution algorithm should have the information, or it should use the temperature values of all the neighboring points. So if in 2D there will be 8 neighboring points, if I divide this into rectangular grids or square grids, we'll have 8 neighboring points, right? So our solution algorithm should include the temperature for those 8 neighboring points. Okay. Why? Because information can travel in all directions. This is not the case for other types of equation, as we will see later. Okay. So another point is that for this type of problem, we need to provide boundary conditions over the entire boundary. So here these are the boundaries, right? So x equal to 0, this is the x equal to 0 line, x equal to some final line, y equal to 0, and y equal to some final line. So at all these points, so the entire boundary we need to give boundary condition. This is not true for other types of problem. We'll see later that for other types of problem, we can only give conditions at one side, or we cannot give also. Okay. So, but in this case, it is needed. Boundary condition. I should not say we cannot give. I should say that it is needed or not. In this case, boundary condition is needed for all the boundaries. So this is an example of an elliptic problem. Okay. So what is the main thing that we should take from here? We should we can summarize that for an elliptic problem, the information from any point passes to all the other points in the domain instantaneously, and the information from all the other points also pass to this point instantaneously. Okay. So let us go to another example. Any questions here? So it is not very clear what are characteristic line from this example, but it will be clear from the next example. Okay, what are characteristic lines? Next and next to next example. Okay, no questions. Let us to take a look at another example. Okay. 1D unsteady heat conduction equation. Conduction is diffusion, so 1D unsteady diffusion equation. So 1D unsteady diffusion equation can be written like this: del U del T is equal to some constant A into del square U del X square, where U is the dependent variable and T and X are the independent variable. T is the time and X is the spatial direction. Okay. So for example of 1D unsteady diffusion equation is 1D unsteady heat conduction. Okay. Del T is equal to alpha del square T del x square, where alpha is the diffusivity, small t is the time, and x is the x coordinate. So it is one dimensional because there is only one spatial dimension, one spatial direction. But there are two independent variables because there is a temporal direction also, time direction. So two independent variables, time and space x, and temperature T is dependent on both these independent variables, time and space. So again, if we go back to our classification, this equation we can write in this form: alpha del square T del x square minus del T equal to 0. Please switch off your mics. Here's feedback. If you keep switch on your mic, it creates a feedback sound if you are not using a headphone. So for this equation, A is equal to alpha, B is equal to 0 because there is no del square T del x del y term, and C is also 0 because there is no del square T del T, not del x del y, sorry, del x del T term, and C is equal to 0 because there is no del square T del T square term. Okay, so we can write this as A equal to alpha, B equal to 0, C equal to 0, or B square minus 4AC is 0. Okay, 0 minus 0. So it's a parabolic equation. Again, the same question comes. We have found that this is a parabolic equation. So what? You are saying, you are claiming that this is a parabolic equation by showing some calculation. But what is the physical significance that of the fact that this is a parabolic equation? What more understanding can we get based on the nature of this equation? Okay. So let us take a look at the domain of this problem. So domain of this problem is, so there are two independent variables. So we can define the domain in terms of the two independent variables. So in the x direction, say the x direction, the domain is from 0 to L. So let us consider a physical case to understand this better. Okay, there is a rod or a bar, okay, 1D, which we can consider as a 1D domain. Okay, 1D rod or a bar or a stick, okay, metallic bar. So which is of length L. And we want to only find the temperature variation with time and with along the length of the bar. So the length of the bar is along the x direction, and we want to find the variation of temperature along the length of the bar with various time. Say we have given some condition that the time, the temperature, the boundary is different. So initially the entire bar is at 300 Kelvin, but at time t equal to 0, we have specified that the one of the ends of the bar is at a higher temperature, say 500 Kelvin. So we want to find out how the temperature changes with time and space. So in this case, the domain is between 0 and n in the x direction. And in the time direction, the domain starts from 0 and say it is up to some t last, because we want to calculate up to some time. So we want to find the temperature variation up to some 1 minute or say 10 minutes. So t last is 10 minutes. Okay. So in the time direction, it is from 0 to t. So in the y-axis, I am plotting the time, and in the x-axis, I am plotting the x spatial direction. Okay. So now let us consider that this problem. Let us consider that the metallic bar was there, and at time t equal to 0, we have given some temperature condition. At some point, let us consider we have not given the temperature 500 at the edge, or we have given it at the center. Okay, at the middle of the bar. So bar is of length L, and we have given at the middle of the bar that suddenly the temperature should be 500 Kelvin, not 300 Kelvin. Okay, and we have given this condition after some time, not at time t equal to 0. So initially the temperature was 300 everywhere for say first 5 minutes. Then after 5 minutes, we have suddenly said that at the center the temperature should be 500 Kelvin. So this can be denoted like this drawing shown here. Okay, so time was propagating from 0 to t, some point t. At this point, the temperature, at this point, the condition is given by this red dotted line. Okay, we are at this condition. So The space variation is along this line and the time is at this point. Okay. So now we have introduced the disturbance. So this disturbance is introduced at somewhat like the middle point of x between 0 and n, and at that time, whatever is the time at that point. Okay. So what will happen? We know physically what will happen, right? Once we introduce the disturbance, so with time now the temperature will change in all the neighboring points of the rod, right? So what will happen is, because the temperature is higher at the center, the neighboring points will also increase in temperature, and it will, so gradually there will be a gradient that will be set up in the rod with time. Okay, it will take some time to do that. Okay. However, we also know that, means it is trivial to us based on our common sense, that this temperature cannot influence any information in the past. Okay, this new disturbance cannot change anything which has occurred in the past. Okay, so if we consider that this is the disturbance, okay, so this will influence all this region. So this can influence all the x direction region, right, from 0 to L, but only the time region which is ahead of this point of time. This disturbance cannot influence any region which is before this time. Okay, so the bottom part, which is not shown here by dashed line, which is the clear space, cannot be influenced by any disturbance at point P. The only region which can be influenced by this point P is what is shown by the hashed region, okay, which goes from length 0 to L and from time T to T last. Okay, so only the future can be influenced, obviously, and the past cannot be influenced. That is our common sense. Why? Because we know that time travels in only one direction. Okay, so time is like a one-way coordinate. So we can only influence the future if some change occurs at a point. We cannot influence the past. So it means that, so in this form we call it that the domain of influence of P. Okay, this domain of influence of P is this domain shown here by the dashed region or hashed region. Okay, this is the domain of influence of P. So this is the region which P can influence. So we will define two terms. One is the domain of influence and one is the domain of dependence. Okay, for any of these physical problems, we need to understand what is the domain of influence and what is the domain of dependence. Domain of influence is the region which can be influenced by any perturbation. Okay, so for this perturbation or change that is occurring here, the domain of influence is all the space between 0 and L, but only the time in the future, not the time in the past. This is our domain of influence. If some changes had occurred here, okay, let me just use this one on this. So if some changes occurred here, okay, then its domain of influence would have been only the region ahead of this point, right? It would have been only the region ahead of this point. So wherever the perturbation occurs, it will define the domain of influence. So it would have been only this point. If some change had occurred here, the entire region ahead of this would have been the domain of influence. Okay. So it seems like there is a line which demarcates the change in behavior. Okay. So ahead of this line, we can influence the solution. Below this line, we cannot influence this solution. This line is known as the characteristic line. Okay. This line is known as the characteristic line. Okay. So we can only influence the solution ahead of the characteristic line in this case. Below this characteristic line, we cannot influence the solution. Obviously, the characteristic line will depend on where the perturbation is done. So in this case, the characteristic line is this. If I use the perturbation here, this characteristic line is this. Okay. So it is a demarcation in time, but there is no differentiation in the space direction. Okay. So actually, this type of problem although we are calling it as parabolic problem, actually this is only parabolic in the time direction. This behavior is only valid in the time direction, right? In the space direction, it is still similar to our previous problem. Like this point can influence any other point in space. So in space, this is still an elliptical problem, but in time, this is a parabolic problem. So a better way to state that, some books will say that it's a parabolic problem, but a better way to state this problem is that this problem is parabolic in time and elliptical in space. Okay. Let us try to summarize or see what I have written here. So t is a one-way coordinate, can only influence the future if some change occurs at a point. This type of problems are also called time marching problems. Okay, it will be clear later. The solution of this is much easier because any point here will only influence the next point. Like any point ahead of this can only be influenced by the points before this, not the point ahead of this. Okay, so we can just march along. We can start from some initial solution and then we can just march along time. Okay, at every time we can find a new solution and we can delete the previous solution. So we only need to store value for 2 time steps. We can delete all the other solutions. This will be clear later on that. Solving these problems are much more easier. Okay, these time marching problems. There's a discontinuity across the length of time when the disturbance is given. This discontinuity is not in the temperature. Okay, this discontinuity is the second derivative of temperature. It is important to note that the entire problem is not parabolic. I have already explained. Only the variation with time is parabolic. Variation with respect to space is still elliptic in nature. Okay. So if say after a long time the problem reaches a steady state, it means that there is no change with time. Okay. So if there is no change with time, del t term will go to 0, and we will be left with del square t del x square. Okay. So this will become a elliptic problem. Although from here directly you cannot use that b square minus 4ac to show that it is elliptic because there is no other terms here, but still it is an elliptic problem. Okay, you cannot show this using b square minus 4ac as our conditions are valid for only 2D problem. This has become 1D problem in steady state. In unsteady it was a 2D problem because there was one dimension of space and one dimension of time. But in steady state this becomes a 1D problem, but still remains elliptic, but you cannot use b square minus 4ac to show that. Okay, so again to summarize, this is parabolic in time and elliptic in space. These are also called as initial boundary value problem. The previous elliptic problems that we have discussed are known as boundary value problems because the boundary conditions define the problem. Here, in time, the initial condition defines the problem. In space, the boundary conditions define the problem. Let us come back to this again. Okay, we will go to case 3 in the next class. Where are the conditions needed here? Okay. So for space, x direction, we have to give conditions at x equal to 0 and x equal to L. These are the boundary conditions. Okay. So in this domain, the boundary conditions looks like this line. Okay. Because the space, the temperature at this point can vary with time also. So the boundary conditions are along this line. Similarly, the boundary conditions at L are along this line. So x equal to L, but time can change. So the temperature at the boundary can change. What about the time condition? We have to give a condition at the initial state. Okay, for all the x values. So this at the beginning of the domain, at the bottom of the domain, for all the x values from 0 to L, we need to give some temperature condition. Okay, so this is denoted by this region, x going from 0 to L, but time t equal to 0. What about the other end, t last? Should we give any condition there, or can we give any condition there? What will be the value at t last? Like for our elliptic problem, also the domain looks similar, but we were giving condition for all the 4 edges. Here we have already given condition for this edge, and this edge. What about the top? Can we give any condition there? Boundary condition?
No, sir.
We cannot give. Obvious. This is obvious because this is in future. So we do not know. This is part of the solution. We do not know what is the what are the values of temperature there. We are trying to find that value. Okay. And even if we knew the value there, that value cannot influence the past. So any value here cannot influence anything in the past. So there is no point in even if somehow like we knew that. Obviously we do not know it, but even if we specify something here, that should not cause any change in any of the previous time. So that should not cause any change in the domain. Okay. So that's why there is no condition needed. So only one condition is needed for the time direction. Okay. For parabolic problems, only one condition is needed, the initial condition, and elliptic problems, all the boundary needs conditions. Here there are two boundaries, this needs condition. Okay, boundary condition. Another concept here is that already I have defined what is domain of influence. Okay, there is another term called domain of dependence. It will be clear in the next example, but here let me just explain. So this point P, the value at this point P. So what changes where? So if some change occurs anywhere in the domain, here the domain consists of both x direction and time direction. So at which locations can the change occur so that the value at P can change? If I make some change here, okay. If I make some change here, I don't know whether you can see the mouse cursor or some lag is there. I am locating a point very near to T last. Okay. So will this point influence the value at P? Will this point influence the temperature value at P?
No, sir.
It cannot, right? Because it's in future. So what are the locations which can influence the value of P?
The locations below P.
The locations below P, correct. So all the locations to this location. So this entire region can influence the value at P. Okay. So this is known as domain of dependence of P. Okay. The value of P depends on this region. Okay. Any perturbation given here will influence the value of P. But any perturbation given ahead of this will not influence the value at P. So this is the domain of dependence of P. P depends on these values. And domain of influence of P is where P influences the values. Okay. So ahead of this characteristic line. So this characteristic line divides, in this case, it divides the domain of dependence and domain of influence. So is this clear? What is domain of dependence and what is domain of influence?
Yes, sir.
For this physical, yes, for this physical problem, it is very clear because time, we know that time can only travel in one direction. Now it's a philosophical question why time only travels in one direction, or why we cannot influence the past. That we cannot discuss in this course, or there is no concrete solution also. A lot of philosophical debates can happen why time is a one-way coordinate but space is a two-way coordinate. But that is a matter, another matter. But from our experience, we know that time is a one-way coordinate, and for one directional, like the variation can only occur in one direction. So influence can only, something can only influence the future, cannot influence the past. So for that type of problem, the domain of influence is given like this, and domain of disturbance is given like this. Okay. It is not always. I don't know whether I have another example in future, maybe in the next class. I have already prepared this notes, sir. Prepared long back. I think another one question. I don't think I have an example, but just to let you know, or just to consider this case, say there is a flow in a pipe. Okay. Now this flow in a pipe is occurring, and I don't have this example. Let us just discuss this verbally. Okay. Suddenly it came to my mind. I did not plan this. So the flow in the pipe is occurring at a very small velocity. Okay, they say it is very small velocity. The flow is going on in the pipe at a very small velocity. If I at any point in the pipe or tube, if I drop a drop of ink, if I introduce a drop of ink, okay, what will happen to the drop of ink? say the limiting case is that velocity is very negligible. The flow is occurring at a very small velocity. What will happen to the drop of ink? How will it travel? In what directions?
It will diffuse in all directions, sir.
It will diffuse in all directions, correct. So we'll see that the ink is spreading in all directions. Okay. It's like our elliptic problem, right? So now say the velocity becomes very high. Okay, the velocity is very high. Okay, the flow is coming at very high speed through the tube. Now again, I have introduced the same drop of ink. Now what will happen?
Diffusion happens only along the flows.
It is not diffusion. Okay, diffusion should have happened in both directions, but here diffusion is negligible as compared to convection or advection. So the flow is carrying the ink. You are correct in saying that the movement will be only in one direction, but the technical term is not correct. That diffusion happens. It is actually advection that is, or transport is occurring in only one direction, in the direction of the flow. So it is as if that information or that disturbance that we have introduced can only influence the y direction or say x direction in the tube, the direction which is downstream of that point. It cannot put any influence, it cannot influence any point before that point, right? In the case of very high speed flow. So even for spatial problems, you can see that it is behaving like a parabolic problem for the case that I am just describing. So because the disturbance is only influencing the future part, not future means in the downstream part, and it is not influencing the upstream part. So in the x direction itself, it is behaving like a one-way coordinate. Okay, it is not that there is, it's a time dependent. You know, the x direction itself also can behave like a parabolic nature. So what will be the domain of influence and domain of dependence in that case?
Is my example clear? Did you understand what I'm trying to say?
Sir, the direction of flow, like the direction in which the flow is occurring, will be the influence, the domain of influence.
From
And
that point, yes.
Yeah, from that point.
And before that point, the upstream side from which the flow is coming is the domain of dependence. So any change that is occurring in the upstream side will influence that point, right? So if I introduce another drop of ink beforehand, that will influence that point. So that is the domain of dependence. So what I was trying to say here is that it is not only time which can behave as a one-way coordinate. Okay, even space can behave as a one-way coordinate, like a parabolic nature. So in those cases, again, we can use matching type of solution, and the solution will become much easier. We can just proceed from the left-hand side of the domain and try to calculate what is happening on the right-hand side, because we know that right-hand side will not influence the left-hand side. Okay, so this is the. So I hope this makes it more clear. Okay. Now, just before, so we will finish this class today. Let us revisit the previous problem. What is the domain of influence and domain of dependence in this problem? This point P is the point where we have introduced the perturbation. So this is an elliptic problem. So what is the domain of influence and what is the domain of dependence and why? If a question comes like that, and that explain the domain of influence and domain of dependence and explain why is it the domain of influence and why is it the domain of dependence. What will be your answer?
So domain of influence will be in all direction, I think.
In all directions. So what is the area in all directions? The entire domain or some small domain or something like that?
Sir, entire domain.
Entire domain, correct. Because P can influence the entire domain. Any change at P can influence any, like all the points in the domain. So P, because P influences the entire domain, the domain of influence is the entire domain. So for an elliptic problem, the domain of influence is the entire domain. What about domain of dependence?
So entire domain.
Entire domain. Okay. What is the logic behind that? Correct. Your answer is correct.
Because the whole domain is influenced. Any change in the domain influencing the point P.
Correct. So because any change anywhere can influence the point P. P is dependent on the entire domain. So the domain of dependence of P is the entire domain. So for elliptic problems, the domain of influence and the domain of dependence are the entire domains, unlike parabolic problems, which we have seen. that the domain of influence and domain of dependence are different. Okay. Let us stop here, and in the next class we will see some more examples. We'll see a hyperbolic case, then we will see some
Sir,
other
I
cases.
have a doubt.
Tell me. Yes.
Sir, in case of parabolic equation, the line separating the domain of influence and domain of dependence, that line will come under which domain?
That is the characteristic line. Okay. So it will not.
Okay.
So it does not have any thickness. Okay. It is not that like it has some thickness in the t direction. So it is just a hypothetical demarcation between the domain of. So the domain of influence and domain of dependence are touching each other. You can say. It is like a hypothetical line which is just dividing those two domains. Okay. It is not a separate domain. It's called as characteristic line. Line does not have any thickness, right? So it is just like a say all the points that are present along this direction. It does not come in any domain. Okay.
Yes, sir.
Or you
Okay,
can say
sir.
that it comes in like it will come in both the cases. I mean, any change that is happening here will influence any change along this line also. So that's why it is part of domain of influence. And any change that is happening on this line will also change the P. Okay. So it also comes as domain of dependence.
So it means that if I have a closed region, suppose
Yes.
my domain is closed. So
Hmm.
in case of parabolic equation, my domain of influence and my domain of dependence are both closed also.
Yes. Yes.
Okay, sir.
If the
Okay.
time is direction is not finite, then this will be, you can go, means the domain of influence will be any time beyond this
Yes,
point.
sir. Yes.
Okay.
Okay. Thank you, sir.
Okay. So let us then stop here, and we will continue this discussion. In the
Sir,
next
I
class.
have one question.
Yes, please. Ask.
Sir, like this characteristic line which we are drawing here, so it is based on this time coordinates, or we can say that since time is our one day, like it
One-way
goes in the
coordinate.
one direction.
Yes. Yes.
So, is there any other example where time is not that thing? Like when we simulate something, then this time will not determine us which domain is our influence domain and which one is the dependent.
Good question. So if it is a, so there can be two cases in a problem. The problem is independent of time. Okay. In that case, as I was saying, it can be an elliptical problem or a parabolic problem, or depending on, say, I was giving that example, right? That flow case. So I will come to your question later, but let me just first explain. So if the flow velocity is very high, although it is not time dependent problem, we can see that the point actually demarcates the influence, the domain of influence and domain of dependence in the pipe, or the example that I was giving of ink drop. Okay. So even if there is no time variable in the problem, we can still have separate domain of influence and separate domain of dependence, depending on other nature of the, like, nature of the problem. In that case, the nature was that the flow was very fast in one direction. So now coming to your question, if it is a time dependent problem, if there is variation with time, there has to be like, you cannot say that, like, because of the nature of time, the time in the future cannot influence anything in the past. Okay, there can be no problem where some change in the future is going to change something in the past. Okay, so if it is a time dependent problem, there always has to be a demarcation between the current time, like at the current time, between future and past. So if it is a time dependent problem, you always have to have a characteristic line which demarcates the future, the domain of influence and the domain of dependence, because of the nature that time cannot behave in a two-way way, like a two-way information. Like, the information cannot pass in two directions, because always the information can only pass in one direction. If a problem depends on time, it has to be like this. Okay, what I have just shown here. Okay, if then the other case can be that the problem is not dependent on time at all, then it can behave in both ways. But if it becomes a dependent, if it is a problem which is dependent on time, you cannot escape the fact that the domain of influence will be ahead of the time and domain of dependence will be before that time, because information cannot pass in the other direction in time. Is it clear? So you cannot artificially also construct any problem where the time becomes like a two-way coordinate, because we know that past cannot be influenced. Okay.
Yes, sir. That part is clear. Like, but is there any some kind of practical example where we make this domains without like which doesn't have some time influence into?
Yes, like that problem, elliptic problem itself is without any time. So any steady state problem is without any time. Any other types means. So there are many examples like our 2D steady state heat conduction equation that is not dependent on time. What the first example that we have seen.
Yes, sir.
They are,
Yes, sir. That was my follow-up question. So, like, since as you said, this if our whole system is in steady state, then this whole thing is not dependent on time. So, like, as you said earlier, like that from our characteristic equations, we can determine that whether our domain has some kind of discontinuity or not. So, like in case of this steady state, we are like not accepting the fact that we are having some kind of discontinuity. Like, for example, in the diffusion problem, you said that when our system will be time independent type of problem or the steady state occurs, then the whole thing will become or then the whole domain will work like a elliptic type of equation. But mathematically we cannot determine that. So
why not? Means I did not understand your
like
question.
mathematically still we have this A as alpha and B as 0 and C as 0. So technically B square
that is because it has become one-dimensional problem. Okay. So that also can be classified. The way we have classified is for a two-dimensional problem, b square minus 4ac. Okay. So this type of classification is only valid for two-dimensional problem where both x and y are there. So what you are saying is that say, let me go to that. Because this was a 1D problem, and if the unsteady term goes to 0, we are only left with d square t dx square equal to 0. So here we are not able to use our classification technique b square minus 4ac. Okay, but still this is elliptic because the nature is still elliptic. Means the behavior is two-way. But if it is a 2D problem, it is still like I'm not clear about your question. Means
sir, like you first mentioned that when we describe something in terms of a partial differential equation, then the higher order terms determine the characteristic equation of our whole domain. So in this case, since this temperature is dependent upon x and small t, so the characteristic equation will only be determined from this alpha d2 t by dx square term. So that's my point. Even if we are neglecting the time
I
thing.
understand now. No, actually, what is happening is that ideally we should call this as elliptic in space and parabolic in time. Okay. So for the time, this the nature is determined by this term, and for the space, this is determined by this term. So what the way of this the classification that we are showing, this b square minus 4ac, this is a very limited way of doing the classification. Okay, it does not capture all the different types of equation. This is only valid for a particular condition, 2D, then second order type of PDEs. Okay, so this is just one way of showing the classification, but actual classification we need to understand based on the physics. Okay, based on the physics of the problem. So although if you want to apply the equation for this equation, if you want to apply b square minus 4ac, you will find that it is looking like a parabolic, like b square minus 4ac will be 0. Okay, but because it is a different problem, we cannot use that b square minus 4ac type of classification here. Okay, we know based on the nature that this is an elliptic problem. So it is better to approach the problem based on the nature, whether the behavior is showing elliptic behavior. When we will call it as an elliptic behavior, when the disturbance can influence all the direction, and all the directions can influence that point. And when we will call it as a parabolic problem, when the point can influence only in one direction, and only one direction can influence that point. Okay, so it is a better way to understand. So now, for preliminary analysis, people just study it using this b square minus 4ac, but that is only valid for that limiting condition that it's a two-dimensional equation, two-dimensional second order PD. Once it becomes either if it is not second order, if it becomes first order, then also we cannot use that. Or if it becomes not two-dimensional, if it becomes one-dimensional or three-dimensional, then also we cannot use that b square minus 4ac type of calculation. Okay, but the nature is still true, and the characteristic lines still hold. Means the discussion about the characteristic lines.
Okay, sir. Got it.
Any other questions? Very, very good. This type of question should be asked because it clarifies also the doubts of other students.